Okay, so the IMO has recently taken place, and today we are going to get into its first problem, fresh out of the oven, which is of course is easier problem 1. Okay, a line in the plane is called sunny if it is not parallel to any of the x-axis, y-axis, and the line x plus y equals 0. Let n greater or equal to 3 be a given integer. Determine all non-negative integers k such that there exist n distinct lines in the plane satisfying both of the following. So those two has to be fulfilled. For all positive integers a and b with a plus b less than or equal to n plus 1, the point AB is on at least one of the lines and exactly k of the n lines are sunny. Okay, so our aim is to find different values of k. For starters, let's try to understand the problem better by playing around. This is not a bad strategy, so let's get started with the smallest case, n equals 3. So let's just draw out our table. And we know that a plus b has to be less than or equal to 4. So it can be 3, 1, 2, 2, or 1, 3. Okay, since it has to be non-negative and positive, it can't be 0. Okay, so now we have the rest for 2, 1, 1, 2, and 1, 1. It will make a triangular pattern, and let's just label it, which will greatly help us. Now let's play around with our model and try to get a k equals 0 with all lines being parallel, which is just done as follows. All of them are parallel to the y-axis. So let's try k equals 1 now. We can do the fancy method of this one, or we could do the more chaotic, crazy, but still valid method of drawing 2 sunny lines and another line with the final dot. Any orientation you want. That's not sunny. For k equals 3, why k can't be equal to 2, we'll explain on that later. That this is just warming up. We can have this possible configuration. And now we are done with warming up. Let us get into the proof-based analysis for this problem. Okay. So first we'll start by drawing our grid, which will have a triangular pattern, and let's assume n has to be greater than or equal to 4. This will become apparent later on. So let's say this is an n equals 6, and now we are trying to prove a claim, which will be a very important when we are trying to continue later. Not all of n lines can be sunny. So that means there has to be at least one line which isn't sunny, and the maximum amount is k minus 1. Let's try to prove that this is false for the sake of contradiction. Okay, let us first remember our boundary conditions, which are n has to be equal to 6, so we can't have any more lines or less lines. Now let's start with our proof. Because of this, none of the points on a non-sunny line can be connected by one line, which means these 6 points, 1, 2, 3, 4, 5, 6, that 6 points which are just parallel to the x-axis, and y equals minus x. And since the maximum is n equals 6, there has to be a bijection, which just means that a point on the blue line has to connect to a point on both the green and yellow line, on a straight line of course. So let's just try by connecting them. We can obviously see the solution of 1, 1. But what if we have another point? Well, we can't make that. That's not a straight line. We can't do that. That's not a straight line. And this will just be parallel to the x-axis. So, as you can see, this claim is clearly not false, and it is true. Okay. So, knowing this, we can conclude for n greater than 4, k has to be less than or equal to n. There can't be more than n amount of lines. So we can also know the maximum is n minus 1 for k lines. Now let's go on to a more rigorous proof, which uses a technique called induction. So let's start off with an arbitrary case. Let's fix that line real quick. Let's start with an arbitrary case. You can see here that n equals 7, but let's imagine it's infinitely, well, not infinitely, but a lot of n. It doesn't have to be a set amount. And we can start our plotting for n. Okay, so let's try. There will at least be one non-sunny line. Mistake there. And wait, let's just fix that line because it looks horrendous. And now we can officially start with that row. Since there's to be one non-sunny line, it could be that row, and they'll bring us to the n-1 case. n-1 has the same amount of sunny lines because there are n-1 non-sunny lines. And we can get n-1 by crossing any of the lines shown here because they are all non-sunny lines. Okay, so by this, you can probably already see where this is going. We go to the n-1 case, and we can basically repeat the same process, which we just show here. Since there will be one non-sunny line, this line, that line, and we do this on and on and on until we go to our base case n equals 3, which in this case we have already previously talked about to some extent. This method is called induction, where we use a lower base case to prove a higher base case because they share similar intrinsic properties. Okay, now let's finally get on to the proof. Okay, wait, let's just write that first. K equals 0, and now k equals 1. We can do as we showed before, the cool looking more scarlet curve. And let's just go to k equals 3, which we also have shown before. But why not k equals 2? What is wrong with k equals 2? Well, so let's first define what are the possible sunny lines that can exist on this plane. This, and this. Okay, so for k equals 2, we want two sunny lines. So let's say we choose this line and that line. Now that leaves 2 points which have to be connected by one line, and the line connecting them is a sunny line. So it is 3 sunny lines. And by that we have proven the first question of the IMO 2025 by induction, and that all n's has k equals 0, 1 and 3.